Well, good morning, good afternoon, or good evening again. Here we go again. We are looking at computational strategies for the various arithmetic principles. And so I'll go back to the first two slides of our PowerPoint presentation that you have access to on the D2L site. But the title is Computational Strategies for the Arithmetic of Whole Numbers. And we're going to continue on our journey to look at the computational strategies for the arithmetic principle called division. And remember, there's two types of division. Before we do that, let me remind you once again, arithmetic principles, addition, multiplication, subtraction, and the two kinds of division give rise to a set that we want to find the size of. And in class and in these video presentations, we've been calling that special set the target set. It's the set we want to identify and then find the size of it. Now, identifying the target set that we want to find the size of is one step of the process, but the second step is after we find that target set, how big is it? What strategy or computational calculations, computational strategies can we use to find the size of that target set? So in reading this second slide, just to remind everyone in our audience where we are, recall that arithmetic principles or combinations thereof lead to a special set whose size we wish to determine, and we've been calling that the target set. Very quickly, recall that for the arithmetic principle called addition, there would be various sets, all with a common unit of measure, and we're wondering if we were to take all these sets or these groups of objects with this common unit of measure, if we were to bring them all together into a common group called the target set of the target group, what is its size? That's the principle of addition. Multiplication is the same thing as for addition, except the requirement is in these groups for which the objects all have a common unit of measure. Before we bring them down into a common group or a single group called the target set, we want to observe that all the groups have the same size. And that's the difference between multiplication and addition. Multiplication, all the groups that we're getting ready to combine together all have the same size, whereas in addition, the sets don't necessarily have the same size. Then in subtraction, we are given a single set of objects, and we're wondering if we reach in and pull out a portion of those objects from the original set. Remember, the original set's called the minuend set. And when we reach in and pull out a portion, that set that we're pulling out is called the subtrahend set. When we pull those objects out, the set that remains is our target set. How many objects that remain in the minuend set after we remove that subgroup or that subcollection of objects called the subtrahend set, how many remain? And that set called the difference set, and its size is called the difference. So there are the arithmetic principles called addition, multiplication, and subtraction. Now we're going to turn our attention to the arithmetic principle called division, except there's two types of division. So here on this slide you see a picture or a collection of, once again, those darn beach balls or those colored balls. And we're starting out with a collection of objects. And this collection of objects that we're starting out with is going to be called the dividend set. And the dividend set is a set of objects that we want to partition, separate into smaller groups according to a rule. In partitive division, the rule is this simple. We specify a number of groups on the front end. And looking at this picture, partitive division, you'll see that I have 4 empty groups, and this is a generic grouping. So it could be 4 boxes, it could be 4 bags, it could be 4 kids that we're going to distribute the beach balls to. And we're wondering if there are 4 groups, 4 objects, 4 sets, 4 kids, and we want to distribute the beach balls to these, how can we do it so that they are distributed in a fair way, in an even way, so that each kid ends up with the same number of beach balls, or each box ends up with the same number of beach balls, or each bag ends up with the same number of beach balls. So in partitive division, we start with a set called the dividend set, and I want to separate it into smaller groups according to a rule, and the rule is I'm going to specify on the front end how many groups there are. So in this little clip, in this advancement, notice I'm going to distribute one at a time, which is what kids would do on the playground. If these were 24 pieces of candy, and there were 4 kids, they would start distributing the 24 pieces of candy or 24 cookies to each kid one at a time. And so in this animation, you see me distributing them one at a time. But all of a sudden, the kid says, oh, I'm down to half the size I started with. I've already distributed 3 cookies, 3 beach balls, 3 pieces of candy. I'm going to go ahead and distribute the rest of them 3 at a time. And so now I've emptied the dividend set, and I've made the observation that all the items, all the objects in each of the 4 groups have the same size. Now, in partitive division, that's the answer we're looking for. Any one of these 4 groups actually represents the target set, because I want to know how many balls, how many pieces of candy, how many cookies each one of these kids got, or each one of these boxes contained. And in this case, they'll just count 1, 2, 3, 4, 5, 6, and they see that in each set, any one of these being the target set, there are 6 beach balls or 6 cookies or 6 pieces of candy. So you'll notice in our notation, our abstract symbolism to represent this, we have 24 divided by 4 is equal to 6. Let me look at that and talk about that just a little bit more, and simply say that we started out with 24 beach balls, and we're going to use this notation, and I'm going to distribute the 24 beach balls or the 24 cookies or the 24 pieces of candy according to the rule where I have 4 groups. And what I want to know is, when I get finished, what's the size of each of those groups? So in partitive division, what we know is we have a given set of objects called the dividend set, whose size is called the dividend, in this case 24. And we know the number of groups that we want to separate the 24 beach balls into. In this case, it's 4 groups. So this particular number here that's telling us how we want to separate those 24 objects, it's called the divisor. And the size of the first set, the set we're starting it with, is called the dividend, and its size, or dividend set, and its size is called the dividend. So here's the divisor, the 4, and the dividend's 24, and I want to know, after I've separated those 24 objects evenly or fairly into those 4 groups, what's the size of each group, and that will be our target set. In this case, our answer turned out to be, when we got finished, that we distributed 6 beach balls to each of the 4 kids from the 24. Now we can check to make sure that the answer is the right answer, the 6 beach balls, because I know the number of groups I started with, it's 4, and I know the size of each of those groups, it's 6, because that's the answer we were looking for, the size of the target set, 6, and Piaget's conservation of numbers says, if I take those 4 groups of beach balls and put them back into the dividend set, I better recover all the beach balls I started out with, for which there were 24. So 4 times 6 is 24. And so this confirms that the division we performed, or how we obtained the size of our target set 6, that 6 is the correct answer, because 4 is the number of groups. So here's the number of groups, and the 6 is what we discovered, size of each group. And by putting those 4 groups together again, each of size 6, I've got to recover the 24 beach balls that I started with. So with partitive division, once we perform division, because of the relationship, intimate relationship with multiplication, we see that we can check our answer. So if we started out, instead of 24, if we started out with 48 beach balls, and we divided it by 4 kids, then we would go through a process and find out that each of the kids received 12 beach balls, and we can confirm this because if 4 is the number of kids and 12 is what we believe to be the answer, then if we put those 4 kids and the number of beach balls that each kid has, put those together, we better be able to recover or get back to the original dividend set or the size of the dividend set, which is 48. So this is the important relationship that we want to remember with respect or between division and multiplication. Now, what we're looking for, how do we find the size of these target sets? What computational strategies will kids begin to go through starting in kindergarten, first grade, second grade, and as they continue up to working with larger numbers, they've got to find, or you call in what we talked about in class, there's really only 2 things you're helping your kids do, you with all the other teachers from kindergarten to 5th grade. You collectively are helping your kids do 2 things. What are they? Count and measure in increasingly faster, more efficient, more sophisticated ways. So when we start talking about these computational strategies that kindergartners and first graders might use for partitive division, those strategies are going to change. They're going to become more efficient, more sophisticated because the numbers are getting bigger. So the strategies they use in kindergarten, first grade are not the same strategies they're going to be using in the 3rd, 4th, 5th grade. And so we want to look at some of those earlier strategies. Again, remember the terms that are associated with division, and we've been talking about partitive division, but for division there is a dividend, that's the size of the set we start with. There's a divisor, that's the number of groups we're going to separate the objects of the dividend set into or by. And then there's that answer called the quotient. So it's the size of each of the groups, okay? So any one of those groups could be the target set, but it's the size of each of those groups because they're all the same size. We haven't talked about remainders yet, but we'll talk about remainders through the course of either this video or the next video. So we have a dividend divided by a divisor, and we want to know what the quotient is. And there may or may not be a remainder, but we'll talk about that shortly. Before we go any further, I want to remind you what we talked about in class is that usually for addition, multiplication, and subtraction, the types of objects or the units of measure have very little to do on the size of the target set. However, in division, the types of objects can impact the size of the target set substantially. Here's a couple of examples. Remember that the objects in the dividend set, or for that matter, of any set of objects, whether you're working with addition or multiplication or subtraction, but particularly for division, the objects in the set fall into 2 categories. They're either discrete or they're continuous. Now, what do we mean by discrete objects? Discrete objects are those for which you cannot continually break apart into smaller and smaller pieces so that it makes sense. On the other hand, continuous objects are those for which you can continue. You can split it in 2, and you can split it in 2, and you can split it in 2, or split it in 3 parts and split it in 3 parts. You can continually make them smaller and smaller, or break the sizes up into smaller and smaller parts. So toy cars, those are discrete objects. Footballs, those are discrete objects. Because why? Cutting up a football makes little sense. Cutting up toy cars makes very little sense. But there are things breaking up into smaller parts that do make sense, like cookies. We can break those up into smaller parts. Cupcakes, sheets of paper, liquid objects, we can break those. So there is a difference between discrete objects and continuous objects. So we're going to look at a couple of problems. Problem one says share 5 toy cars evenly between 2 kids. And problem 2 says share 5 cookies evenly between 2 kids. So let's look at that. The first problem 1, you recall I had 5 toy cars. That's my dividend set, and 5 toy cars is the size of the dividend set. And what I want to do is I want to, as best I can, share those 5 toy cars evenly among 2 kids. So here's the first kid, and here's the second kid. And so if they're out on the playground, here's how they begin to share them. I might pause and say this. My opinion is that of all of the arithmetic principles, addition, multiplication, subtraction, division, the two kinds, partitive and quotative, I believe that division is the first arithmetic principle that kids encounter, because it's the one that they're it's sort of forced upon them when they're like 2 and 3 and 4, and that's to share things. So they start taking things they have and sharing with their friends or with others. So they start sharing, and they start sharing as they would as a 2-year-old, a 3-year-old, and a 4-year-old, one at a time. So in this particular picture where I've got 5 toy cars, they'll start sharing them, and I won't draw the toy cars. I'll use dots. They'll put a toy car here, and 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 they will look back up in their set, and they'll see they've got one toy car left. So the question is, what will they do with this toy car? Well, it makes no sense to cut it in half, okay, because then you no longer have a toy car. And so in this particular situation, they'll have a toy car left over. It's going to represent the remainder, okay? So when 5 toy cars are distributed evenly among the 2 kids, each kid gets 2 toy cars, and that's the answer to the question, and there's 1 toy car left over. Now, problem 2 is you don't have 5 toy cars, you have 5 cookies. And now you're going to distribute those to 2 kids. And once again, they'll go back to probably distributing the cookies one at a time. So they'll distribute a cookie here, and a cookie here, and a cookie here, and a cookie here. They'll look back and see that they have a cookie. Now, these 2 kids are smart. They're not going to, let that cookie just sit there and nobody take their cookie. What they're going to do is they're going to split the cookie in half, and so this kid will get a half a cookie. This kid will get a half a cookie. And in this problem, there's no remainder. Each kid's going to get 2, and although we haven't talked about fractions yet, kids start learning what 1/2 means as early as the first grade, and this kid gets 2 1/2 cookies, so there's no remainder. Now, in both of these problems, symbolically, we would represent 5 down as the size of the dividend set, divided by 2 kids, and that equals what? Okay, so what is the answer to this problem? Well, if we don't know what the nature or the types of objects in the dividend set are, we can't answer this. We don't know if this is 2 cookies with a remainder of 1, or whether this is 2 1/2 cookies. And in the absence of knowing the nature of the objects in the dividend set, we can't determine the right answer. So it's very, very important when you're working with division problems or working with the subject of division that your kids understand, there's 2 types of divisions, and in both cases, the nature of the objects in the dividend set impact or affect how you're going to answer this particular problem. So here's a problem with discrete objects, toy cars, and here's a problem with continuous objects, cookies, and the answers are different in those 2 cases. So now we want to go back to looking at our list of computational strategies for partitive division. So again, remember, types of objects in the dividend set are very, very important in how they impact the answer to the question. So when you're starting working with division problems, think about what are the nature of the objects in the dividend set. Are they discrete or are they continuous? And as I've already said, usually, most of the time, this has no impact on answers to problems that have to do with addition or multiplication or subtraction. But in division, they have a lot to do with, so it's something we have to pay very close attention to. So let's look at our list of computational strategies for a part of division. Again, I have listed at the top in red numbers, red numerals, types of problems that kids might encounter up through the 3rd grade. You see 21 divided by 7 is what number? What's the size of the target set? Or 72 divided by 9, what's the size of the target set? Or 91 divided by, and now we're looking for the divisor. 91 divided by what number is 13? or 732 divided by 16 is what number. And the way we approach these problems, of course, depends on the grade level, our experience, and our understanding of computational strategies. So again, I'm going to take you back to what kids learn on the playground and perhaps in kindergarten or first grade about the subject of sharing or subtraction. And the first one we're going to look at is one called repeated subtraction. We want to think back. How do kids start sharing evenly or equally or fairly on the playground when they're sharing objects? And again, it could be discrete objects or continuous objects. Again, so your answer depends on the types of objects in your dividend set. So I want to look at a problem where the dividend is of size 15, or the dividend set has 15 objects in it, and 3 is the number of groups we want to divide these objects into. Now remember, we're talking about partitive division, and in partitive division, we know the number of groups that we want to separate the objects from the dividend set into. What is the unknown in a partitive division problem is the size of each of those groups. Once we get finished distributing those objects evenly from the dividend set, what's the size of each of those groups? And so that's what we're hunting for here. Again, one of the early strategies, one of the first strategies kids use when they have these 15 objects and early on we don't make too big a deal out of the fact that these are discrete objects or these continuous objects, but in that elementary, those two problems that are fairly elementary, you can show your kids in first grade why the nature of the objects in the dividend set makes a difference. In some cases there's a remainder, and in some cases there is never a remainder, especially in the setting where you have continuous objects in the dividend set. So I have 15 objects and I want to distribute those fairly or evenly into 3 groups. And the 3 groups, this is generic. The dividend set, we need to know the units of measure. That's very, very important. 15 object could be 15 toy cars, 15 cookies, whatever. But I'm going to distribute those evenly across 3 groups. It could be 3 boxes, 3 bags, 3 kids. This could be 15 toy cars, how to distribute those evenly or fairly among 3 kids. And so they'll start distributing them. And so they'll very quickly get rid of 3 of those objects. So they're going to come out here and say, okay, I had 15, I got rid of 3, so I'm down to 12. So I know I have distributed to each of the kids one of those 15 objects each, but I got rid of 3 of them. And then I'm now down to 12. Now I'm going to subtract 3 more because I'm going to distribute 1 more to each of those 3 groups. So now I've gotten rid of 3 more, so 12 minus 3 is 9. And so I've done this a second time. So here I got 1 object distributed to each one of them, another object distributed to each one of them. So it's 3 objects at a time because there are 3 groups. And then I'll go 9 minus 3, that's 6. So I distributed another object. And then 6 minus 3 is 3, distributed another object. And then finally, 3 minus 3 is 0, and I distributed another object. So I look back through my list of subtractions, I'm going to end up getting rid of 5 objects to each of those 3 groups or each of those 3 kids. So if I started out with 15 toy cars, each kid gets 5 toy cars each. If I start out with 15 cookies, each of those kids get 5 cookies each. Now this strategy is called repeated subtraction. And even though I did it in groups of 3, they'll start off doing it one at a time, but when they complete that first task of distributing one at a time, they know that because there are 3 groups, they got rid of 3. So they'll get rid of 3, that gives them 12 left, get rid of 3 more, that gives 9 left, get rid of 3 more, 6 left, and so on. So this is called repeated subtraction, pretty easy to follow, and this is the one kids will use early to answer a question that has to do with partitive division. So we've taken care of repeated subtraction. So repeated subtraction I may have said repeated division, but repeated subtraction is a strategy for answering the question, if I take a set of objects called the dividend set and I want to distribute those evenly across a number of sets, a number of groups, and I do that fairly so that each group is the same size when I get finished, we can do that through a strategy called repeated subtraction. It's a strategy that actually begins on the playground but comes into the kindergarten and first grades. The next strategy is called sequential counting, and this one is basically the kid just simply goes through and distributes all of the objects so that everyone has the same number of objects. Then they count the size of any one of those groups, and that determines their answer. So let's see what I mean by that. So let me look at the division problem. 33 divided by 5. And let's suppose that there are 33 cookies, and I want to separate them or divide them evenly among 5 kids. So I've got 33 cookies. And I want to divide those evenly among 5 kids. So here are my 5 kids, and the cookies should be distributed. What will kindergarten or first graders do? They'll just start separating the 33 cookies, and they'll go 1 for you, and 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 1 for you. Now, they're eventually going to get to the point where they get rid of all the cookies except 3 of them. So they know so far they've distributed the cookies. They don't know the answer to the problem yet. Okay, they don't know how many cookies each of the kids are going to get. But what they do know is they've distributed those evenly, and they've got 3 cookies left. Now, what are they going to do with those 3 cookies? Well, if it were 3 toy cars, there's not much they can do. They've got, each of the kids got 6 toy cars, and there's 3 toy cars left over, and there's no way to separate those discrete objects into smaller parts or smaller pieces, so that those 3 toy cars can be distributed evenly among the 5 kids. But for 3 cookies, they can. Okay, and let's just think about this for a moment. They'll take 1 cookie, and they'll take a cookie, and they'll somehow figure out a way to divide it into 5 equal parts, and they'll take each of these 5 parts and they'll put each of those 5 parts up there. Then they'll repeat that for the remaining 2 cookies, and so when they get finished, each of the 5 kids has the same amount of cookies. They have 6 cookies, and since there were 3 cookies, each one got, and you'll eventually know this is, they'll get a 1/5 of 1 cookie, then a 1/5 of another cookie, and then a 1/5 of the 3rd cookie. So in each of these, they will get 6 cookies, and they'll get a 1/5 of 1 cookie, a 1/5 of a 2nd cookie, and a 1/5 of the 3rd cookie. So when we get finished this problem, the answer turns out to be that if there are 33 cookies, each kid will get 6 and 3/5 cookies, and there's no remainder. Now, I said this is representing the computational strategy called sequential counting. So what was I talking about, or what was I thinking? Well, they would distribute everything, and so when they got finished distributing, now they would go and find out, well, how much cookie did each one get? And they would start counting. 1, 2, 3, 4, 5, 6, and a 5th, and a 5th, and a 5th is 3/5. So they counted sequentially to arrive at the answer of 6 whole cookies, and then a 5th plus a 5th plus a 5th, which is a really sequential counting, is 3/5 cookies. So each kid gets 6 and 3/5 cookies. So sequential counting is essentially you perform the distribution. You empty the dividend set, so that you've distributed the items in the dividend set, whatever they may be, discrete or continuous, in such a way that they are distributed evenly. And then you go into any one of those groups. Any one of those 5 groups in this case is the target set. You can pick any one you want. Why? Because they're all the same size. You distributed them evenly, so any one of the groups is the same size, so any one of the groups can play the role of the target set. So you just go in and count any one of the groups, whether it's the first one, second one, third one, fourth one, or fifth one. So that's sequential counting. That's the strategy called sequential counting. Okay, let's go back to our list. So in our list, we talked about repeated subtraction. We talked about sequential counting. What's this notion of combination pairs from combination pairs for multiplication? Well, let's look. 30 divided by 6. And I want to know what the quotient is. Remember, the quotient is the size of any one of the sets that you get when you distribute 30 objects among the 6 groups. Now remember, we're in partitive division. In partitive division, what you know is the dividend set, and your divisor is or represents the number of groups that you want to separate the objects in the dividend set into. In fact, this is the reason I call this external division, okay? Or group division is I know the number of groups, okay, and I'm doing it externally. In other words, the way in which I'm dividing the objects, the 30 objects of the dividend set, I'm doing it out of a process in which the objects or the groups are external or separate from the dividend set. Remember, in partitive division, the units of measure for the dividend set have nothing to do with the units of measure in the divisor set. This could be 30 toy cars, and the 6 could be 6 kids, or it could be 30 cookies, and the 6 could be 6 bags, or 6 boxes, or 6 kids. But their units of measure really have nothing to do with each other. So I want to talk about what I mean by combination pairs. Well, recall that whatever this answer is, whatever the quotient is, that's the size of each group. So it must be the case that 6, the number of groups, times the size, better get you back, or you better be able to recover the entire dividend set, which in this case is 30. So 30 divided by 6 is what quotient is the same problem as 6 times what number is 30. Now kids are starting to learn their multiplication facts beginning in the 2nd grade. So this turns out to be what we think of as a combination pair for multiplication. 6 times some number is 30. 30 is a friendly number, so this is a combination for a pair for multiplication. So combination pairs for multiplication give rise to combination pairs for division. So they'll know that 30 divided by 6, certainly by the time they get to the 3rd grade, that 30 divided by 6 is going to have an answer of 5, because they know that since 5 is the size and 6 is the number of groups, that answer is correct, because 6 times 5 is 30. So we get combinations for division because we know or remember or recall our combinations for multiplication. So we know that if we have, let's say 40 divided by 8, they'll know that because 40 divided by 8 gives rise to a number, they know that 8 times that number better get me back to the 40. And they know this certainly by the time they get to the 3rd grade, so they'll know the answer that the size of each group better be 5. And so in the division problem, 40 divided by 8 better be 5. So again, combinations for multiplication give rise to combinations for division. And going one step further, compatible pairs for division are those that are derived from compatible pairs for multiplication, which are precisely the multiplication facts, or those number pairs that come from multiplication tables. So if we know, for example, 4 times 6 is 24, and that's a multiplication fact. It's not a combination pair because 24 is not a friendly number, but it's a compatible pair for multiplication. They know that 4 times 6 is 24. They're beginning to learn it in second grade, but they're certainly in Tennessee going to know it by the end of grade 3. But if 4 times 6 is 24, this actually gives rise to 2 compatible pairs for division. Because remember, this one comes about if I take 24 and separate it into 6 groups, we know the size of each group ends up being 4, and the reason I know that is 24 divided by 6 is 4, and that's the same as 6 times 4, which is 24. And remember, we know this is true, and we can draw a picture of why that's true. So even though this first problem right here, 4 times 6 equals 24, means there are 4 groups, each of size 6. If I put those 4 groups together, each of size 6, I get 24 in the target set. The same is true if I have 6 groups, each of size 4. If I put those 6 groups together, each of size 4, I come up with 24 objects. So 24 divided by 6 is 4, because 6 times 4 is 24, and 24 divided by 4 is 6, because 4 times 6 is 24. So multiplication facts give rise to division facts. So for example, if I know that 7 times 8, what is it? 7 times 8 is 56, and that's usually one of the harder ones for kids to recall. And of course, they don't have to recall it. They can use a backup plan to recover that one, and that's discussed in another video. But 7 times 8 is 56, and so this gives rise to 2 division problems. It says that 56 divided by 7 is 8, or 56 divided by 8 is 7. So any multiplication fact gives rise to 2 division facts. And again, by the end of 3rd grade, when kids learn all their multiplication facts up through 12, they are going to know from their table a substantial number of division facts. And these are very important when we start looking at division problems which involve numbers that are much bigger than 1 and 2 digits. If they start involving numbers which are 3, 4, 5 digits, we better have a faster, more efficient, more sophisticated way to find the size of the quotient set, find the size of the quotient set called the quotient, other than repeated subtraction, sequential counting, or knowing our combination pairs or our compatible pairs, because there are going to be numbers that are not compatible pairs for division. Even though we may not know that what the answer to this problem is, if we happen to know that 9 times some number is 631, if I knew this, I would know the answer to this one. But 9 times some number 631, that's not a compatible pair for George, and may not be a compatible pair for any of you out there. So I can't quickly write down what the quotient would be for 631 divided by 9, because I don't know what 9 times what number gives me 631. Okay, so where are we in our list of computational strategies? That brings us down to Subitizing, and Subitizing really includes all of our combination pairs and our compatible pairs for division. It's just those kinds of division facts that when we look at them, we know their answer to them immediately. So let's see if I can give a couple of examples of that. So Subitizing which I also call recognition counting, always worry when I start writing something down, am I spelling the word correctly or not? And so I'll be honest with you, I may get to a point and say, man, I don't recall how to spell this word. I do remember I was struggling in the second, third grade with spelling. And my dad kept me from going out to play for about a week, and I had to learn my spelling words. And at that point in time, I started figuring out, man, there must be a better way to learn how to spell than try to memorize and start. So even before phonetics was in vogue, I was starting to figure out there's got to be a way to figure out how to spell things. So I turned out by the time I was in the 7th or 8th grade, I was a pretty decent speller. That doesn't mean I'm not misspell some words during these video sessions, or certainly mispronounce words. But let me not to get too far straight here. So subitizing is just recognition counting, and it's things that when we look at, we know the answer to immediately. So again, when you say 12 divided by 3, kids by maybe towards the end of the 2nd grade, but certainly 3rd grade, they're going to know that 12 divided by 3 is 4. They're going to know that 24 divided by 4 is 6. And so these are emerging because they've subitized multiplication facts, and so these division facts come out there. So subitizing actually includes the combination pairs plus the compatible pairs. I'll call them compatibles. So subitizing includes the combination pairs and compatibles, but remember the compatible pair list differs from kid to kid after they leave the 3rd grade. Some of them, because of their experiences, know certain things because of their environment. I think I talked about this in class the other day. You may not know this one, but if you take 52 and divide it by 13, some kids are going to know the answer to this because in a deck of 52 cards, they know if they distribute all the cards evenly among 4 people, they know each one gets 13 cards. Or if they take and divide it among 13 people, it gets 4 cards. So they know that 52 divided by 4 is 13. So for some kids, those are 2 compatible pairs of division problems to which they quickly know the answer to. And that's all subitizing is that they look at an arithmetic expression or arithmetic problem, and they know the answer without doing any really formal calculations in their head or on paper. They just know the answer. It's called recognition counting. Experience, and repeated work with something, they finally figure out, or they are able to recall immediately what the answer is to an arithmetic expression. In this case, we're talking about division. So now we've talked about subitizing, we've talked about compatible pairs, division facts. So subitizing actually includes both combination pairs for division and compatible pairs for division. It's just recognition counting. They've done it so often, so many times, hopefully in a happy environment, in a learning environment, in a discovery environment, they've discovered, I know the answer to this. I don't have to do any work. I don't have to think about it. I know the answer. I'm going to talk just a little bit without illustrating mental math. But mental math, remember, is just the ability to take not huge numbers, not large numbers, but relatively small numbers, and because the kid understands what division means, in this case partitive division, they can take a problem and they can actually manipulate the numbers in their head without putting them down on paper. So it's actually just, mental math is just the ability to do some calculations in your head without recording the details of it on a sheet of paper. They do the calculations in their head and they arrive at the answer. It might be if they take 100, okay, and they want to know what happens if they divide 100 by 20. Well, depending on what steps the kid goes through, they don't have to write this down on a sheet of paper. They could say, well, let's see, 20, 20, 20, that's 60, 20 more, that's 80, 20, that's 100. And I did that 5 times, so I know that 20 fits into 100 5 times. Or they may say 40, 100 divided by 40. They know it'll only go in there twice because 2 40s is 80, and I've got 20 left over. But mental math, actually, the ability to perform mental math comes from experiences, understanding the concepts associated with the arithmetic principles, addition, multiplication, subtraction, and right now partitive division. And they perform that arithmetic in their head. We are not talking about big numbers. We're not talking about large numbers. We're talking about manipulating arithmetic for small numbers in their head. Now, one thing I do believe is that mental math, or asking your kids to participate in or perform mental math, really begins to emphasize their understanding or underscore their understanding of place value, because place value plays a very important role not only in all of our computational strategies, but certainly in the ability to perform mental math. So I'm not going to say much more about mental math, but essentially mental math has to do with performing arithmetic on small numbers, relatively small numbers, in your head without doing all of that work on a sheet of paper. And that's all it is. And it could involve, math tricks or math gymnastics or whatever. But that's all mental math is. So let me talk about the next computational strategy for division, and it's called decomposing the dividend. Let's see, what does that mean? Let's look at a division problem. Say 91 divided by 7. And so if I have 91 toy cars and I want to divide those evenly among 7 kids, or I have 91 cookies and I want to divide those evenly among 7 kids, or I want to put them on plates, there's 7 plates, I want to put the 91 cookies on 7 plates. When I get finished doing that or performing that task of separating the dividend set 91 evenly onto the 7 plates or in the 7 groups or in the hands of 7 kids, how many objects, how many cookies, how many toy cars does each kid get? Well, now this transition from concrete to abstract is one that should be made, slowly, deliberately, and make sure that when we move from a concrete setting, which I have to, and my numbers start to get larger, when I move from a concrete setting to an abstract setting, we want to make sure that when we move to the abstract setting, the kids understand what's meant in a concrete setting. So we want to make sure that they can go back and forth between concrete conceptual understanding and abstract conceptual understanding. So in this problem, 91 divided by 7, I would want to know that a kid, your students, could make up a word problem, which is to contextualize this problem and say, this problem could mean I've got 91 toy cars and I want to share them evenly between me and 6 of my friends. So I want to separate it into 7 groups or in the hands of 7 kids. Or I've got 91 toy cars, 91 cookies, and I want to divide those evenly among 7 kids, or put them into 7 bags so that the same number of cookies are in each one of the 7 bags. Or I've got 91 candy kisses, and I want to divide those evenly among 7 kids, or I want to put them into 7 bags. I don't know how many kisses go into each bag. Or I want to put them on 7 plates. But I want the kids to be able to understand what this problem is asking. I don't want them to look at it and it just look like a cold arithmetic expression. I want them to put some substance to it. They actually know what this means in terms of a real world problem, what's being asked. So turning this into a word problem, which is called contextualizing, is very, very important. Usually in a word problem, we're trying to decontextualize it, get an arithmetic expression like this, which represents what's going on in the word problem. But right now I have what's called a naked number arithmetic problem, and I want to know how to perform the arithmetic so as to find the size of the target set without having concrete objects in front of me to manipulate. So what I'm going to do is I'm going to take the 91, and since this is probably not a compatible pair, meaning kids know the answer to 91 divided by 7 immediately, one of the strategies you might introduce them to is one where they take the dividend and they separate into parts or pieces that are very friendly with respect to 7. Now remember, for addition, multiplication, and subtraction, friendly numbers are usually those numbers that end in 0 or 5. But in division, friendly numbers take on a different meaning, and they don't necessarily end in 0 and 5. For in this problem right here, I know that I can divide 7 into 70 very quickly. It goes 10 times. So I might take the 91, and I might peel off 70 from it. And if I peel off 70 from it, that leaves 21. And so I might ask myself, can I divide 7 into 70 and then into 21? And the answer is yes. And so I'm dividing this by 7. So I've changed the problem from 91 divided by 7 to 70 divided by 7. And once I get finished distributing those 70, I've got to turn around and take the 21 that I have left, and I've got to distribute those among the 7 kids, and I'm going to want to know what that answer is. Now, this makes sense in terms of pictures, and I'll show you that in a minute, but notice that 70 divided by 7, that's an easy quotient. It's a compatible pair. And 21 divided by 7 is 3. That's easy. So I know that the answer to the size of my target set is 13. That means if I've got 91 toy cars and I want to distribute those evenly among 7 friends, each friend gets 13 toy cars. Or if I have 91 cookies and I want to distribute those or put those onto 7 plates, then each plate's going to contain 13 cookies. So this is called decomposing the dividend. I separate the dividend by addition into components, each of which are friendly with respect to the divisor. And this strategy works very well, up through the numbers that the kids are comfortable with in their multiplication tables, which is 12. But when you get bigger numbers than that, we'll need another strategy. So it works best to use decomposing the dividend when the divisor is single digit. So this is called decomposing the dividend. And remember, decomposing means to take a number and separate it by the addition symbol, separate it into components so that each of those parts, when put back together, give you the original number. And so this is called decomposing the dividend. Now I said I was going to show you a picture, and let me get to a new. So here's my dividend set, and I started with 91. And I want to separate it into 7 groups. And again, it could be 7 kids, it could be 7 plates, it could be 7 bags, it could be 7 boxes, it could be 7 cars, it could be 7 houses. But I want to take these 91 objects and I want to begin distributing those across these 7 groups in such a way so that when I get finished, the size of all those groups is the same. It's identical. And I said, I'm going to show you a picture of what it is that I just did. I said I took the 91 and I split it up into 2 groups, 70 and 21. So instead of distributing the 91, I'm going to distribute the 70 and the 21. Notice once I get finished distributing the 70 and get finished distributing the 21, the answer to each of those problems put together gives me the quotient that I'm looking for. Well, it turns out that 70, I know how to distribute those among the 70. They get 10 here and 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 10 here. And then the 21, I'll go back and distribute those across the 7 objects, and I'll put 3 more in here and 3 more in here. And 3 more in here, not saving much room for the addition symbol. 3 more in here, 3 more in here, 3 more in here, and 3 more in here. And so that tells me that this strategy of decomposing the dividend set into 2 or more parts, I can take each part and distribute those across the groups and do it for each of these parts, and I come up with the correct answer. So 13 is the size of each of those 7 groups. In other words, if it was 91 cookies, each of those 7 kids gets 13 cookies. If it's 91 flowers and I'm distributing those among 7 vases, each of the vases will get 13 flowers, and so on. So this strategy is called dividend decomposing. Let's look at another example. Let's take 524 and divide it by 4. And so again, this is a naked number arithmetic problem. It's a division problem. We don't even know whether it's partitive or quotative division because there's nothing in there that would indicate that it's partitive or quotative division, other than George told you from the beginning of this video session that we're talking about partitive division right now. So this is 424 objects that I want to figure out a way to distribute evenly into 4 groups. So again, we want your kids to be able to contextualize this, meaning make up a word problem for which this is the arithmetic principle that might have emerged. Well, it could be 524 pennies. I'm going to put those into 4 piggy banks. How many pennies goes into each piggy bank? Or it could be $524. I want to share those. This may be $524 that a father has. He has 4 kids. He wants to know if he distributes the $524 evenly among the 4 kids, how much money does each kid get? So, how can we do this using the strategy of dividend decomposing, or decomposing the dividend? Well, I suppose the first thing, now again, these strategies that I'm sharing with you, they're personal, okay? So when I look at a problem like this, the way I approach this problem might be different than the way you approach this problem or any of your kids approach this problem. I'm giving you a strategy that's not locked down to a set of fixed steps. So they get to be creative. They get to take, like in the number 524, how can I decompose this into parts or numbers that I can easily divide by 4? And it will differ from kid to kid. I'm going to choose an easy one and say the thought process of a kid might be this. 524's got 400 in it, and I know how to divide 4 into 400 quickly. Now, if I've taken 400 away from 524, that leaves 124. Well, 100. I can divide 4 into 100. I know that. And the 3rd graders know that problem. They know what 4 into 100 is, or 100 divided by 4 is. And that leaves 24. And it just so happens that 24 is a friendly number with respect to 4. Now, 400 and 100, granted, those are friendly numbers with respect to addition, multiplication, and subtraction. And it turns out that they're friendly with respect to 4. But 24 is not friendly with respect to addition, multiplication, or subtraction, but it is friendly with respect to the division by 4. So remember, friendly numbers for division differ from friendly numbers for addition, multiplication, and subtraction. So now I go through and I take 400 divided by 4. Add that to what I get when I take 100 divided by 4, and add that to what I get if I get 24 divided by 4. Again, I showed you by picture why it's okay to take 524 and split it up into 2 or more groups. And here I split 524 into 3 groups, 400, 124. In other words, if that was 524 ping pong balls and I was putting them in groups of 4, okay, how many ping pong balls are in each of those 4 groups? I'm going to distribute those by first taking the 524, splitting up into 400, 124, and then taking each of those 3 groups and distributing them across the 4. So the first time I distribute 400 divided by 4, I'm going to put 100 ping pong balls in one of the 4 boxes, each of the 4 boxes. And then 100 divided by 4 is 25. And so I'm going to divide 25 more balls into each of the 4 boxes. And then finally, 24 divided by 4 is 6. And I'm going to divide 6 balls into each of those 4 boxes. And so when I get finished, it's 100 plus 25, that's 125, and 6 more is 5, 130 is 131. So it turns out that I'm going to be able to take 524 ping pong balls and distribute those evenly into 4 groups, and each group's going to have 131 ping pong balls, or 524 cookies divided by 4 kids. Each kid will get 131 cookies and be sick in about an hour. Okay, so again, that strategy is called dividend decomposing, and it works even when there are remainders, because it could be that in this particular problem I could have written 526, and then this would be 26, and what I might do at that point in time is write it as 24 plus 2, go through these steps, and I've got this 2 that's left over. Now again, depending on the nature of the objects in the dividend set, I may have a remainder of 2, or I may not have a remainder of 2. If that's 2 cookies, they're not a remainder, okay? All right, so that's dividend decomposing. Let's look at another strategy. So now we're looking at factoring the divisor. Okay, so I've talked about decomposing the dividend. Now I want to talk about a strategy called factoring the divisor. So let's look at an example. And so we're talking about factoring divisor. We just got finished talking about decomposing the dividend. Well, decomposing means to separate by the arithmetic principle addition, which means it separates components into blocks, which when you put them back together again, gives the original set. So make sure when you talk about decomposing as opposed to factoring, decomposing means to break up into parts or components by the arithmetic principle called addition. Now we're going to talk about factoring the divisor. So let's look at this problem, 156 divided by 12. Now, because the divisor 12 is part of the numbers that can be used in multiplication facts, you could use dividend decomposition to perform this division. That is, separate 156 into parts which you know are easily divisible by 12. You know, for example, they know their multiplication facts, so they might pull off 144 and write 156 is 144 plus 12. And 144 is easily divisible by 12. 12 is certainly easily divisible by 12. And so by using dividend decomposition, we could find the quotient using that strategy. But I want to talk about factoring the divisor. So in factoring the divisor, what I do is I change this problem by writing 12 as a product. That's what factoring means. When we factor a number, it means it separates it not by the principle of addition, but by the principle of multiplication. So I'm not going to write 12 as 8 plus 4, or 6 plus 6, or 10 plus 2. I'm going to write it as a product of two numbers. And let me write it as 3 times 4. Or I could have written by 2 times 6, or 6 times 2, but not as 1 times 12, because then I'm back to my original problem. So I'm going to look at this problem right here, 156 divided by 12, or 3 times 4. Picture-wise, here's what we do. We're starting off with a dividend set of size 156. And so what I'm going to do is, in this particular problem, I'm going to show you why I can change this into 156 divided first by 3. Then when I get finished with that problem, I'm going to go ahead and divide it by 4. So I want to show that 156 divided by 12 can be performed by separating the divisor by multiplication. Now, that's what factoring means. Separate by the principle of multiplication into 3 times 4. And then, instead of forming the division all at once by 12, I'm going to do it in 2 steps. I'm going to divide first by 3 and then divide by 4. Now, why is that a good strategy, or why can that be a good strategy? Well, I'm now dividing by single-digit numbers, not by a double-digit number. In other words, if I had 18, I could write 18 as 2 times 9. Those are 2 single-digit numbers, and I could divide first by 2 and then by 9, and use some of my previous strategies like dividend decomposition to perform that step of the division. Okay, so let me show you why changing the 12 to a 3 times 4 and performing the division in sequence, why that works. Because kids want to know why it works. You want to know why it works, okay? So I'm going to try and do this through pictures. So I'm going to take the 156 and I'm going to divide first by 3. So I'm dividing by 3. Okay, I'm going to first divide by 3. Now, the 156 divided by 3, I can go and I could perform, for example, dividend decomposition. So before I answer this problem right here, the 156 divided by 3, I can say, oh, that's a 150 plus 6. And I know how to divide 3 into this because this is a power 10 number, and I know how to divide 3 into 15. That's 5. So this answer, when I divide 150 by 3, is easy. Then I'm going to divide 6 by 3. That's easy. So that turns out that this is 50. And this turns out to be 6 divided by 3 is 2. So that tells me I could put 52 objects in each of those 3 groups. So 52 goes here, 52 goes here, and 52 goes here. So the first quotient, 156 divided by 3, using dividend decomposition, gave me a quotient of 52. So each of these 3 sets now have 52. Now, I'm down to the problem of, I've already completed this, so I'm now down to the problem of 52. The answer to the first quotient, 156 divided by 3, and now my last step is to divide by 4. Okay, and I want to know what that is. Again, I could use dividend decomposition to do this, and I think I will, because I can take the 52 and say, well, that's 40 plus 12, and I can divide that by 4. And I'm going to do this without formally writing it down. So 4 goes into 40 10 times, and 4 goes into 12 3 times. And your kid's going to do this. They're going to start looking for shortcuts, ways to speed up their procedures or their processes. Watch for them. Be patient for them. Don't be a stickler for too many details. Once they see the strategy and the slickness of the strategy, if they start speeding up the process by leaving out some steps, that's perfectly okay. All right. So they get 52 divided by 4 is 13. So they know that this one, when they divide it into 4 groups, okay, this one, let's see, the 52 got separated into 13, 13, 13, and 13. And notice they don't have to do that over there, because whatever happened here happened over here. You don't have to do that. If you distributed this 52 into 4 groups and got 13, when you distribute that 52 into 4 groups, you'll get 13. And when you distribute the third group of 52 into 4 groups and get 13, you're going to get the same. But this now becomes the answer to the original problem. It says that if I take 156 and divide it by 12, I'm going to get a quotient of 13. So 156 divided by 12 is 13. And I can check to see that 12 times 13, using one of your computational strategies for multiplication, you can do this one. For me, I'd go 12 times 10, 120. 12 times 3, 36, and 120 plus 36 is 156. Bingo. That is the correct answer. Now, this strategy is called factoring the divisor. Let's try another one. Now, again, I've already shown you the picture of why factoring the divisor is a perfectly acceptable strategy. What it can do is take a 2-digit divisor and maybe convert it to a product of 2 single-digit divisors and performing the division in 2 steps by single-digit divisors could be faster than trying to wrestle with a 2-digit divisor. Let's look at another example. Let's take 345 and let's divide it by 15. Again, you could use, if you wanted to, dividend decomposition and divide by 15, because dividing by 15 is not too bad. It's not one of your numbers in your multiplication tables, and so it's probably better to take the 15 and factor it into a product of two numbers which are single digit. So remember, this is called factoring the divisor. And I've shown you by picture why it works. So take 345. What I might do is write this as 345 divided by, let's say 3 times 5. And by taking 15 and factoring it into 3 times 5, I'm going to change this problem to 345. First, I'm going to divide by 3. Then later, I'm going to divide by 5. Then you'll have those kids who say, I don't like that order. I think I would much rather divide by 5 first and then 3. They may want to change the problem to this one. That's perfectly acceptable, because why? 3 times 5 is the same as 5 times 3. And so they're good to go. So we're going to choose the first one, only because I wrote it down first. But some kids say, no, I like dividing by 5. I can do this much more quickly than dividing by 3. And if that's the case, it's their problem. It's their work. Remember the thing we talked about in class? Who's the boss of numbers? Your kids are. You are. So the way you perform the arithmetic, the order you perform the arithmetic in, that's your call. You want to make your kids feel like they are in charge of numbers. They're the boss. Remember Piaget's conservation of number? That's what makes them the boss. Remember, numbers are dead, people are alive. So make sure that living things have control over dead things. So make sure your kids have control over numbers, because numbers are deader than a doornail, okay? But kids are alive, so they have control over this. They have dominion over numbers and the arithmetic of numbers. So I want to perform this arithmetic using that order. Again, how am I going to do that? Well, I'm going to take the 345 and I'm going to divide it by 3. I'm probably going to split off 300. That leaves me 45. I'm going to split that up into 30 plus 15. I'm going to divide that by 3. So now in this problem, I'm dividing by 3 first, and then I'm going to close it out by dividing by 5. So 3 goes into 300 in a very nifty way. It's 100. 3 goes into 30 10 times, and 3 goes into 15 5 times. So the quotient is 115. So when I take 345 objects and I divide them evenly among 3 groups, each group's going to get 115 objects. So that was the first level of division. That's like in the picture, I've got 345 and I divided it into 3 groups first, and each of those groups got 115. Then I'm going to take 115, okay, take 115, and now I'm going to divide it by 5. And I'm going to split this up into 100 plus 15. Why? Because for George, And decomposing the dividend, he knows how to divide 5 into 100 quickly and how to divide 5 into 15, so that's the way he decomposed it this way. Some kids might separate it into 50 plus 5 plus 5 plus 5, or 20 plus 20 plus 20 plus 20 plus 20, and do all of those. You say, well, it takes too much time. Well, remember, who's in charge? The kid's in charge. As long as they understand the strategy, okay, they'll learn how to pick up speed later when they become more comfortable with it, or when their number sense and their number influency increases, they'll be able to do this, such as the way that I'm doing this. So again, 5 into 120, and finally 5 into 15, 3. So when I distribute the 115 into 5 groups, each one gets a 23. So 23, not in all of them now, so that's probably shouldn't have done that. Let me try it a different way. Use a different pen. So I'm taking the 115 and now I'm dividing it into 5 groups. Then I do the same thing for each of the other 115, but once I do it once, I don't have to do it for the other 2. And so when I perform this division, each one of those groups got 23. And so any one of these are the answer. So in our problem, when we started out with the 345 divided by 15, the answer after separating 15 or factoring 15 into 3 times 5, when I went through the 2 steps, the answer I ended up with was 23. And so that's the quotient to that division problem. And remember, I can check and make sure this is correct, because 15, which is the number of groups, times the size of each group, which is 23, when I do that calculation by any one of the computational strategies you've learned for multiplication, when I do that calculation, I better get back to the original size of the dividend set, which means I better get back to 345. So the question is do you? So that strategy is called factoring the divisor. Now it turns out you can actually factor the dividend. So let's look at a problem along those lines. So factoring the dividend. So let me get a new screen. So we've talked about dividend decomposition, and we talked about divisor factoring, and now I want to talk about dividend factoring. So we've already talked about this one. Remember, dividend decomposition is the one where you've got your dividend and you have your divisor, and the dividend's not friendly with respect to the divisor. So what you do is you decompose the dividend, or split it up according to the operation of addition, into pieces, into parts, each of which is easily divisible by the divisor. And that's the general strategy for the dividend decomposition. Divisor factoring is taking perhaps a 2-digit divisor and factoring it, separating it according to the arithmetic principle multiplication, not addition, but multiplication. And by taking a 2-digit factor and separating it into a product of 2 single digits, I can perform the division in 2 steps, each of which is performed by a divisor which is single digit. So I perform the first single digit division, then I'd perform the second single digit division, and when I get finished, the final number I get is the size of the target set I'm looking for. It's the quotient. And pretty slick strategies, but what emerges from these different strategies is a much deeper understanding of the concept of division, the idea of taking a set and separating it into smaller parts, smaller portions, according to a rule that's determined by a number of groups. So remember, in partitive division, you know the size of the dividend set. You know how many groups you're starting with. That's the divisor. What you don't know is the size of each group once the dividend set has been distributed evenly among those groups. So now we're turning to dividend factoring. I'm going to write down an expression that'll sort of indicate to you the nature or the idea behind the strategy of dividend factoring. So I'm going to take a dividend, and I'm going to already have it factored. So I'm going to take 12 times 17. And let's suppose I'm dividing this by, let's say 6. And I want to know if I take this dividend and divide it by 6, what's the quotient? Now, I intentionally wrote the dividend as a product, 12 times 17, because it allows me to show you why what I'm about to do is going to work. I'm going to do it with pictures too in just a moment, but I want you to know why the strategy of taking the dividend and separating it by the arithmetic principle called multiplication, factoring it, why factoring the dividend might be a good strategy depending on the numbers that are given to you. So remember, 12 times 17 is the same as 17 times 12. And the reason I changed the order there by putting 12 in the second position is I'm going to perform the division by 6 on 12, which remember is the multiplicand, and then come back and multiply by 17. Okay? So I'm going to go ahead and finish this problem, and then I'm going to illustrate, with a diagram and with pictures, why this strategy works. So in this problem, it turns out that this becomes 17 times, and now I'm going to move the 12 over next to the 6, and I'm going to perform the division 6 on the 12 rather than on the entire set to start with. So I've rearranged these numbers so that when I divide by 6, the order in which I divide by 6, which is on this second factor 12, remember it was in first position, I moved it to second position, which Piaget's conservation number says I can do. And because it's in second position, I can divide 12 by 6 and then go ahead and multiply by 17. So in this strategy, this one is 12 divided by 6 is 2. Then I have to multiply 17 times 2, or it's just 2 17s, which is 2 10s, 20, and 2 7s, 14, which is 20 and 14, which is 34. So that's the quotient in this problem. Let me show you why that works, okay? And I'll try and use the same screen as to why this works. And let me illustrate this with a simple problem like 3 times 4 divided by 2. Now, in the dividend, I already have it written as a product. In a moment, I'm going to do a problem where the step will require you to factor the dividend first, but here it's already factored because remember, I'm going to illustrate to you or show you why in this setting where I have a product 3 times 4, why it's okay to divide 4 first by 2 and then multiply by 3. So I want to show you why it's okay to do this. I'm going to show you why it's okay to move the second factor next to the 2, perform the division, and then come back and multiply by 3. Calculation-wise, this becomes 3 times, of course, 4 divided by 2 is 2, and the answer is 6. And we know that 12 divided by 2 is 6. Now, I'm doing this with small numbers because, remember, I'm going to illustrate this with a picture. And if I start doing it with huge numbers, I've got to write down a whole bunch of dots, and I don't live long enough to do that. Okay, so again, I'm going to go back to the picture 3 times 4. So again, you could have started out with 12 divided by 2. And then what you decided, well, I'm going to write 12 as 3 times 4 and divide by 2, because you've noticed if I take 12 and write it as a product, and one of the factors I put over on the right next to the 2, and 4, that number is easily divisible by the divisor, that's what I want to accomplish. That's what I want to do. Now, I've already shown you mechanically, algebraically, that this problem right here is equivalent to 3 times 4 divided by 2. And that's what I'm about to illustrate, is why 3 times 4 divided by 2 gives you the same target set as 3 times 4 divided by 2. So here goes. So I'm going to take the 3 times 4, so that means I've got 3 groups. Each of size 4. So I have 3 groups. And they're each of size 4. So that's my dividend. 3 times 4 is 12. So here's my dividend. And what I want to do is I want to separate that into 2 groups. Remember, it says divided by 2. So I want to separate this into 2 groups. So I'm going to do that. So what I'm going to do is I'm going to take the size, which remember that's the second factor, 3 times 4. 3 is the number of groups, and 4 is the size of each group. I'm going to take the size 4 and I'm going to divide it into 2 equal parts. And I do that for each of the groups. So I take the first 4, divide it into 2 equal parts, next one, because remember each of the sets are the same size 4. Divide the next set into 2 parts, the next set into 2 parts. And so I separate in 2 parts. What I want to know is, after I've divided, either one of these 2 groups of dots, either this one or this one, I can use to determine the quotient, because the quotient is 6 dots. I divided the 12 into 2 groups. Now notice that the size of this is 3 groups times 2. So it's really 3 times, and you divided 4 by 2. I've changed it so I'm finding 3 groups, each of size 2, and that's 6. And so that counts the number of, in this case, green dots, but it counts half of the original dots, because remember I had to divide it into 2 parts. And I could do the same thing if this had been a 3 that I'm dividing by. Then probably what I would want to do is not divide 3 into 3 times 4, but put the 3 in the second position and divide 3 into 4 times 3. So in that case, I'd be looking at 4 times 3, dividing it by 3. And the reason I put the 3 in the second position on the 12, 4 times 3, is because dividing by 3, 3 by 3 is easy. Picture-wise, once again, I had this originally. Then I changed the 3 times 4 to 4 times 3. And then I said, let's take the size, which is 3, and divide it into 3 equal parts. And so I did this. And so my final answer divide 3 into 3. My final answer is 4 times 1. Okay, so I divided 3 by 3. That's one of these, any one of these groups. And so now it's 4 times 1, which is 4. And that is what you get when you divide 12 by 3. So that's dividend factoring. Let's try it on another big number, like 135 divided by 3. Now you could either use dividend decomposition, you could use, there's no need to use divisor factoring because it's already 3 and you know it's prime and I can't break it down into smaller parts. But I might be able to use dividend factoring by taking 135 and can I write it as a product where maybe one of the factors is divisible by 3. In other words, if I could figure out a way to write that as a 9 or a 12 or even a 3. Well, it turns out that this is, I think, 3 times 45, I think. Okay, now remember, I'm illustrating this. So if I take 135 and it turns out that I can write it as 3 times 45, and let's say a quick check says 3 times 40 is 120 and 15 more is 135, that's correct. So in this problem, what I can do is switch the order and write this as 45 times 3, then divide by 3. And because 3 goes into 3 1 times, this is really 45 times 1, and so the answer is 45. So when I divide 135 by 3, their answer is 45. Now, this naked number arithmetic, depending on the units of measure in each for the dividend and the divisor, depends on what I write down for the units of measure for the 45. Talked about decomposing the dividend, factoring the divisor, and factoring the dividend. I'm going to talk about one more, which is block or group division. So what's block or group division? So I'm talking about block or group division. Now actually, block or group division is setting the stage for what I'm going to call modified classical long division or modified classical division. And all block or group division is really the idea or the ability that your kids, see inside the dividend set and know that it's big enough that instead of separating it 1 at a time, it can do it 2 at a time, or 4 at a time, or 5 at a time, or even 20 at a time. And so let's look at a group or a block division problem. Let's look at 156 divided by 4. Now, I'm looking at block or group division, but let me remind you as sort of like a matter of review. You could, on this problem, you could use dividend decomposition. I'll just abbreviate it. Or you could take the dividend, you could factor the divisor. Now in this case, the divisor is only a single digit, but it may be that dividing by 2 in 2 steps, divide first by 2 and then by 2 again, might be something that your kids like. So factor the divisor, or finally factor the dividend. So those are the strategies we just got finished talking about or going over for partitive division. Now I want to talk about block or group division. And let's begin to use symbolism that's going to be similar to the symbolism that you've already been using, for ever since you were in the probably 4th or 5th grade. And so what I'm going to do is I'm going to write something like this. And this is, of course, a traditional or a classical way to indicate the dividend, the 156, and separate it from the divisor, the 4. Now again, as I said, block or group division is the idea that instead of distributing 156 items 1 at a time into 4 groups, maybe the kid knows that, my dividend set is big enough, 156, that I know that 4 easily fits into 156 a certain number of times. In other words, they know that, for example, they could take... They know 156 is big enough that they could, for example, distribute 10 objects from the 156 to each of the 4 groups. So let's suppose they did that. Let's suppose that they know that 156 is big enough that I can distribute 10 objects to each of the 4 groups. Okay, and if I do that, I will have gotten rid of 40 of the 156 objects. So I've removed 40. I've removed 40, and so I'm going to go through the process of getting rid of that 40, and when I do that, that's 116. Now let's just look at the picture. What is it that I've done so far? I've taken the 156 objects and I have distributed those. Let me do it over here. I've distributed those into 4 groups, and I did it 10 at a time. So I know that if I take 156, it's big enough to distribute 10 to each of the groups, and that's a total of 40. So that's what this arithmetic here illustrates. It illustrates that I've got 4 groups. I know that I can distribute 10 objects to each group, and I know that I've gotten rid of 40 of the objects, and so I've got 116 more objects to get rid of. And they say, oh, that's only 40. I could do that again. I could say 4 times 10 is 40. And I'm underlining the 10 because 10 is the number that goes to each of the 4 groups. And remember, that's part of the number we're looking for. We're looking for the number of objects that go into each group, not the number of objects that go into all 4 groups. We already know the answer to that. The number of objects that go into all four groups is 156. But I want to know when you separate 156 evenly, fairly, okay, into 4 groups, what's the size of each of those 4 groups? So I've now distributed 10, and this gives me another reduction of 160 by 40. Okay, and so now I put 10 more in each of those groups. So this tells me that I've got 20 objects from my dividend set in each of the 4 groups already. So I've actually gotten rid of 80, so I've gotten rid of 40 and gotten rid of 40 more. And remember, I don't believe in borrowing, so I'm going to count up from 40 to 160. 60, it goes from 40 up to 100, and then 16 more, so I know this is 76. I did not borrow, I counted up. Okay, I used a hop, skip, and jump strategy to know that the difference between 116 and 40 is 76. And I say, well, I've got 40 more in there. I'm going to do that again. So I've gotten rid of 40 more. And so now I put 10 more in each one of these. And now I've got 30 in each of those groups, okay? And so I get rid of that. That leaves me with 36. And then I say, I recognize 36. I know that 4 goes into 36 9 times, so I know that 4 times 9 is 36. And so I can get rid of 9 more by putting 9 into each of those 4 groups. That gets rid of 36. And so now I'm left with no objects in the dividend set, and I got rid of 9 more. And now I know the answer to the problem, because in 3 steps I distributed 10 to each of the 4, so I went 10, 10, 10, and then in the 4th step I didn't have enough to distribute 10, but I didn't have enough to distribute 9, so now the answer is 39. And that's what's in each of those other 3 groups, other 3 sets. So now my quotient turns out to be that 156 divided by 4 is actually 39. So if I distribute 156 cookies among 4 kids, each kid gets 39 cookies and then gets sick later on in the day. Okay. Now this is called blocker group division. It's really repeated subtraction, but I'm doing it in larger blocks instead of doing it 1 at a time or 2 at a time. Your kids get more comfortable with using bigger chunks, bigger blocks, bigger groups. So let's let's do another one. 344, and let's divide by, let's say, 8. And I won't know what the quotient is. I don't want to underemphasize the fact that when kids look at 344 divided by 8, I don't want them to look at that just in totally an abstract situation or setting. I want them to be able to say, where would such a problem come from? Okay, how do I contextualize this? I've used this word. Let me go ahead and write it down. Contextualize, which is sort of taking the abstract to concrete or words. In other words, you're making up a problem. I have 344 cookies, and I want to divide those evenly into 8 bags because I'm going to sell them, and I want to know, how many cookies are in each bag. So I want your kids, when they see a problem like this, you should be able to ask your kids on the fly, make up a problem from which this is the arithmetic that would emerge from that problem, so that they don't lose sight of the relationship between the conceptual concrete setting and the abstract setting that we get them in because the sizes of the numbers are getting bigger. We want them to be able to go back and forth between the concrete and the abstract. We want them to be able to not only decontextualize out of a word problem into mathematical symbols, we want them to be able to go the other direction. Take a mathematical expression such as the one we're looking at and make up a word problem for which this is the mathematical expression that would solve that word problem or answer the question that was asked in that word problem. Now we're talking about the arithmetic strategy called group, okay, or block division. So again, beginning to set the stage now for modified classical division, I'm going to use the symbolism that you are used to, and I want to start separating the 344 objects into the 8 groups, okay? So it might be that kids are comfortable enough, they may see, for example, because of the power 10 arithmetic, they may see, wow, I may be able to get rid of 30 cookies all at once. In other words, 344 is big enough that if I'm going to fill 8 groups, I can take 30 cookies or 30 objects from the 344 and separate those into the 8 groups. So this becomes 240. So if I take the 344, it's big enough that I can take out 8 groups of size 30 and put 30 objects in each of those 8 groups, and it won't go over the 344. So again, if they're comfortable in the 3rd grade with their power 10 arithmetic and their multiplication of 8 times 3, they know that 8 times 3 is 240. I'm going to underline this because the 30 is what was distributed in each of those 8 groups. So I have gotten rid of 240 objects. By distributing 30 objects to each of the 8 groups, I got rid of 240 of the 344 objects, so I'm left with 104 objects. And now I want to distribute into the 8 groups the objects that are out of 144. Well, I can't do 30 of them. I could do 10. So I could say, let me take 8 times 10, and that gets rid of 80. Okay, so 8 times 10 is 80. So I'm putting 10 into each of the 8 groups. I've already put 30 into each of the 8 groups. That means between the 30 and the 10, I have 40 objects distributed to each of the 8 groups. So that's part of my quotient. 40 is part of my quotient. I want to find the rest of it. So this gets rid of 80. And quickly you see by counting up, 80 to 100 is 20, and 4 more is 24. And so I have 24 left to get rid of, but I know that 8 fits into 24 very quickly 3 times, so I know that 8 times 3 is 24. So I distributed 3 of those objects to each of the 8 groups, and that got rid of 24, which is the last of the dividend set. So it turns out that these numbers together go into making up the quotient, and the quotient is 30 plus 10 is 43. So I know that 344 divided by 8 is 43. And I can check that out because remember, there are 8 groups. We think the size of each group is 43. If I multiply that together, I better get back to my original dividend set, or the size of my dividend set, which is 344. So the question is, if you do that arithmetic and get an answer, is that answer 344? If it isn't, then there's something wrong with your work. But once again, this illustrates the computational strategy for partitive division that's called block or group division. And I'm now setting the stage for what's called modified classical long division. And before we talk about that, we need to talk about estimation. Okay, if we don't have exact arithmetic and we're just really wanting to get an estimate on the quotient, how can we do that? And that will be the topic of our next video session. Again, setting the stage for long division and getting into the strategy called modified classical long division. That will be the topic of our next video session. Thanks.